Friends, today we will see the applications of finite element to structural dynamics. So finite element method is a very powerful tool and it can be analyzed to solve the problems of structural dynamics. So we can find out the dynamics responses by using the finite element method. The responses such as displacements, velocities, strains, stresses. So these responses are time dependent. So whenever we talk about the dynamics, so all the responses of a structure in dynamics are considered as a time dependent responses. And in structural dynamics, in order to develop the equation of motion, we are going to make use of Hamilton's principle by using Lagrangian equation. So Hamilton's principle, by using Lagrangian equation, we can develop the equations of motions. Now, what is the Hamilton's principle? That means first you try to understand the Hamilton's principle. So here the definition is written, so you just note down this. So it states that of all possible time histories of displacements, that most accurate solution makes the Lagrangian functional a minimum, provided following conditions are satisfied. That is the essential of kinematic boundary conditions, the compatibility equations, and the conditions at initial time t1 and final time t2 in dynamics. Say this principle again, see, it states that of all possible time histories of displacements, that most accurate solution makes the Lagrangian functional a minimum, provided the following conditions are satisfied: the essential or kinematic boundary conditions, the compatibility equations, and the conditions at initial time t1 and final time t2. So this principle, mathematically how the Hamilton's principle is written. So mathematically it is a delta displacements, then integration t1 to t2, initial to final setting, initial and final time conditions, and L dt equal to 0. L is the Lagrangian function. What is L? L is the Lagrangian functional. And this Lagrangian functional is given by T minus pi. T is the kinetic energy and pi is the potential energy. This kinetic energy, we know that it is calculated or is equal to 1/2 integration over entire value x dot t, transpose of velocity. X dot represents the velocity, transpose of velocity into density into velocity into dV. So over entire value we can integrate this in order to find out the kinematic energy. Then we calculate the potential energy by using 1/2 over entire value strain transpose into stress into dV. So equal to, what is stress? Stress is D, that is elasticity matrix, or D into strain, elasticity into strain. So now this is strain transpose D into strain over entire integration over entire value gives us potential energy. That means once we are able to find out the kinetic energy and potential energy, then the Lagrangian functional we can work out. Then what is this strain? Actually, strain obtained from set of time histories. This strain is obtained from set of time histories. And if xi is the generalized displacement, if it is generalized displacement, then we know that the velocity will be d dt of xi. Xi is the displacement, generalized displacement. So their differentiation gives us the velocity. If xi is the generalized displacement, then we state that Lagrangian equation of motion, the Lagrangian equation of motion is given by the dt of dl by dxi minus dl by dxi equal to 0 for I equal to 1 to n. For I equal to 1 to n. So this equation is very important. This equation we can use to develop the equation of motions in dynamics. This Lagrangian equation, we can make the Lagrangian equation, and this equation is derived from Hamilton's principle. Now let's consider the multi-degree of freedom. How the equation of motion for multi-degree of freedom is derived by using this Lagrangian equation of motion. So the notes will be uploaded. I will upload the notes on Google Classroom as well as on Google Drive. Now let's consider finite element form in multi-degree of freedom system. So finite element form in multi-degree of freedom system. So you know very well what is single degree of freedom system, multi-degree of freedom system, etc. So now let's consider 2 degree of freedom system. Just for understanding, consider 2 degree of freedom system. Say spring mass system. Generally we consider, say let's consider a 2 degree of freedom system. Say this is mass 1 and mass 2. Say stiffness of this spring K1, stiffness of this spring is K2, and here the displacement x1 and velocity x1 dot. So displacement of mass 2 is x1 and x2 and velocity is x2 dot. So 2 masses means 2 degrees of freedom system is considered here. Now the kinetic and potential energies can be obtained. So how to find out the kinetic energy? So this is, we know this is 1/2 into m1 mass x1 dot square. 1/2 mx square is the kinetic energy. x1 dot, that is velocity, plus due to second mass m2 x2 dot square. So this is the kinetic energy. Similarly, the potential energy is given by 1/2 k1 x1 square. Now the net displacement is considered 1/2 k2 x2 minus x1 bracket square. So we have now calculated the kinetic and potential energy due to the masses. Now the Lagrangian function is L minus pi. So this is equal to 1/2 m1 x1 dot square plus 1/2 m2 x2 dot square minus this 1/2 k1 x1 square minus 1/2, let's simplify this, say 1/2 k2 x2 square, then this minus minus it becomes plus, it's 2 x1 x2 and this 2 gets cancelled, so it becomes k2 x1 x2 and this is plus x1 square means this becomes again minus 1/2 k2 x1 square. So now next what we have to calculate by using this Lagrangian equation of motion. So what is the Lagrangian equation? Using Lagrangian equation of motion. So this is d by dt into dabba L by dabba x dot 1 minus dl by dabba L by dabba x1. So if we work out this, so differentiation of above with respect to x1 dot, then this is a differentiation with respect to x1. So what we get here, the first equation is say m1 x1 double dot, because this is d of dt, so double integration x1 m1 differentiation m1 x1 double dot, the next plus k1 x1, so differentiation of this 2 gets cancelled, so m1 x1 double dot, next, so x1 dot is only one term, then minus this one half k1 x square minus this minus dabba L by dabba x1, so this is k1 x1, this should be minus. Then next x1 term is here plus k2 x2 and minus k2 x1. So this is the first equation, so this is equal to 0. This is equal to 0. That means this equation now becomes m1 x1 double dot, m1 x1 double dot, then plus k1 x1, then minus k2 into bracket x2 minus x1. x2 minus x1, so equal to 0. Say equation 1. Say this equation is 1. Then d second equation, d by dt dabba L by dabba x2 dot minus dabba L by dabba x2, so this is equal to, now this is 2 m2 x2 dot, m2 x2 dot. Next, this is plus minus plus and plus, okay, then m2 x2 dot plus k2 k1 x1 directly I will do this k2 x2, next is k2 x2 minus k2 x1. So by rearranging we will get this m2 x2 double dot plus k2 x2 minus x1 equal to 0, equation 2. Let's write down this in matrix form. These two equations. So let's write down these two equation in matrix form. So the first equation we get m1 0 0 m2, and the accelerations plus then the second one, the stiffness equation. This is for free vibration, remember. So this is K1 plus K2 minus K2 minus K2 and K2. So this is x1, x2 is equal to 0, 0. So symbolically we can write down m x double dot plus k into x equal to 0. So this is the equation of motion for multi-degree of freedom. So for steady state, if you want to solve this, for steady state, assume solution in the form that x equal to say a sine omega t. So we can assume the solution of this equation x equal to a sine omega t. This is a second order differential equation, and this solution must satisfy the above equation. So it's x dot, that is first differentiation, a omega cos omega t. Again differentiating, this becomes minus a omega square sine omega t, which is nothing but minus a omega square x. Now substituting, because this is the solution, assumed solution, and this solution must satisfy the above differential equation. So substituting above, what we get, if we substitute this, we will get, say, x double dot, that is m here, m, then minus a omega square x. Or that a gets cancelled, let's write down this omega square into x, then minus k into x equal to 0. So here this can be written as omega square. So this is minus actually, this is plus, minus omega square m minus omega square m plus k into x equal to 0. But x is not equal to 0, otherwise solution will not exist. Therefore, minus omega square m plus k must be equal to 0. So this is called eigenvalue problem. So this is the eigenvalue problem. Now we have to solve this, or to find out the frequencies, where omega is the frequencies, and depending upon the degrees of freedom, whether it is 2 degree, 3 degree, 4 degree, so we can find out the frequencies. And for single degree of freedom system, if we solve above, we will get omega equal to root of k by m. The frequency omega equal to root of k by m is for single degree of freedom system. So now see, we have seen that if a given system is a multi-degree of freedom system, then how to find out the frequencies for this. So by using this expression we can find out the frequencies for various dynamic systems, single degree of freedom system or multi-degree of freedom system. Then how to find out distributed mass matrix? Let's consider distributed system, solid body with distributed mass. Say solid body with distributed mass. Solid body with distributed mass. So now we can express the velocity x dot in terms of nodal velocity x dot by using the safe function, where n is safe function. N is the safe function. So safe function can relate the velocity at any point to the nodal velocities. Now the kinetic energy is given by T equal to, by using this 1/2 integration V x dot transpose rho into x dot dV. This we know how to find out kinetic energy. So now this is equal to 1/2 x dot transpose integration over entire volume, substituting safe function n rho n dV into x dot. So this equation, in the above equation, the mass matrix can be obtained. From this, the mass matrix can be given by m is equal to integration over entire value n transpose rho into n dV, or we can write down this in matrix form. So this matrix n transpose rho we can take outside even, it's okay, rho into matrix, set matrix into dV. So using this we can find out the distributed mass matrix. So this gives us distributed mass matrix. Distributed mass matrix. So next time we will see the various types of elements and how to find out the distributed mass matrix. So in dynamics there are two types of problems. Either we have to find out the mass matrix, and two types of mass matrix, again distributed mass matrix or lumped mass matrix, and second one is to find out the frequencies, and for frequencies we have to solve the eigenvalue problems. So most of the time in the examinations for hand calculation, generally the mass matrices are to be asked for various types of elements, distributed mass matrix. And lumped mass matrix means, suppose you have a solid element, say two noded element, and the total mass of the, say this is 1, this is 2, is lumped equally at both the elements. Means if it has a length area L, then the rho, this say M1 and M2. Say for lumped masses, means M1 equal to rho AL is the total mass divided by 2, and M2 is rho AL by 2. So equally it is distributed among the nodes. The masses are equally distributed. So this matrix becomes, say, M1 0 0 M2. So this gives us a lumped mass matrix. However, in order to calculate distributed mass matrix, we have to use this expression. So in a lumped mass matrix, simply the masses are lumped at the nodes equally, and then we can write down the mass matrix very easily. However, in case of distributed mass matrix, we have to calculate by using this formula, integration over entire value, transpose of safe functions into density into again safe function over the entire value. So this gives us distributed mass matrix, and distributed mass matrix gives us accurate results. So as far as possible, the distributed mass matrix is to be used. But for simplicity, sometimes the lumped mass matrices can also be used. So during the next lecture, we will see how to derive the lumped mass matrices and distributed mass matrices to various types of elements. Okay, thank you very much.